All right. So first, thanks, Chelsea, for the introduction. Good morning, good afternoon, good evening, everyone. Depends on where you are. My name is HongyuWu. I'm a professor at Kansas State University. It's my great pleasure today to be here to discuss this increasing critical challenge in the modern power system, cyber-physical security, and also machine learning in this domain. As you know, the power grid becomes more digitized and interconnected, so also becoming more vulnerable to cyber attacks. So I'm also glad to co-present this session with Dr. Bo Liu, an assistant professor at Washington State University, Tri-Cities, and my former student. He's going to dive into some details of his excellent work later on. So here's my outline today. So I'll first provide some research background on the smart grid, cybersecurity, and I will get into the cyber attacks and the defense strategy in the smart grid. Then I will, introduce Dr. Bolio, and he is going to provide some machine learning-based detector and highly stealthy cyber attacks based on his work, which is a challenging, exposed limitation of the current defense strategy. So as we know, the smart grid can be conceptually divided into 6 layers or 7 layers based on how you defined it, based on its interoperability and dimensions. As shown in this figure, the bottom layer of this one is a component layer consisting of power system domains, including equipment and asset of generation, transmission, distribution, and distributed energy resources and customer premise. This layer can also be divided into the zone, including process, field, station, operation, enterprise, and power markets. One layer up, as you can see from this figure, is that the communication layer. So where various communication protocols such as DNP3, IEC 61A50 residing. Another layer on top of the communication layer is an information layer, which has various data and gets stored by the data models. Then we have the function or application layer containing functions such as energy management system, advanced distribution management system, and stuff like that. So one layer up is a business layer that has distinct business objectives, profit associated with various stakeholders. At the topmost layer, as you can see from here, is we have the human layer, right? Which encompasses the policymaker, regulators, operators, engineer, and consumers, all of whom interact with and influence the smart grid through decision-making, regulation, and usage behavior. As you can see, the smart grid is a cyber-physical system where each layer interacts with the rest of the layers. The cyber-physical nature of a smart grid significantly expands its attack surface, making it a primary target for cyber-physical threats. Adversaries can exploit vulnerability across various layers, from hardware component to communication networks to data management system and to human interactions. Between 2011 and 2014, the US Department of Energy received about 362 power interruptions reported related to cyber physical attacks. This basically highlights the growing threats to energy infrastructure. Since then, the frequency and sophistication of the cyber attacks has been escalated. So this slide shows some multiple blackouts from 2003 to 2015 due to cyber incidents. So we have the 2003 Northeast blackout, all the way to Arizona, blackout, and also the 28 Florida blackout. The most famous one, or the well-known one, is the incident in 2015 Ukrainian blackout. So attackers switch off the breakers remotely in the Ukrainian electrical power system with the help of malware Black Energy Trojan. More than 30 substations is disconnected, and 225,000 customers without power for about 6 hours. So the impact was huge. So since the 2015 Ukrainian blackout, the power grid has become a primary target for cyber attacks. So this timeline of this slide showing the major cyber incidents between 2010 to 2020, which reveal a growing frequency and sophistication of those attacks. And notably, recent incidents such as Revel and Enercon demonstrate that renewable energy industry are also increasingly be targeted. This highlights an evolving threat landscape. So I want to talk about some cyber attacks in smart grid. So in our previous work, we categorize cyber attacks into 4 categories. The first category is data availability attack, for example, Byzantine attack and denial of service attack. Since these attacks focus on the communication layer, these attacks are on the IT cyber attacks, which does not directly involve or consider the OT models. So some background of Byzantine attacks. So basically that attack hindered data availability by degrading the communication channel. These attacks are launched by the compromised insider nodes to affect the trusting routing, which in turn reduces overall network performance. Another work which is well known is DOS attack that aims to disrupt the communication between control center and sensor or actuator in the field. DOS attacks are not required to have knowledge of the system configuration to manipulate the control or measurement data in the communication channel. The attack consequence is that system operator can easily notice the attack due to the loss of measurement. However, the operator cannot mitigate the attack since they cannot see the control signal to the actuators. The second category is control signal attack in our previous work. So attack occur basically usually use Trojan to steal credentials, such that attacker can send compromised control signal, sent to the field devices. This malicious and encrypted control will cause physical damage to the field devices or may cause widespread blackout. Third category is measurement attack. The attack compromises the measurement, which is sent to the control center, such that the mislead operator about system voltage, system status, and make mistakes in operation decisions. The fourth category is control signal and the measurement attack. This attack, the attacker basically compromises the control signal, and simultaneously they manipulate the measurement data to cover the ongoing attacks. So this is basically some illustration of different, attack, which is on, based on our categorization here. Next one, I want to introduce some, specific, the attack. The first one, as mentioned before, is control signal attack. The first control signal attack is Aurora attack. The attack introduced by Idaho National Lab, which attacker maliciously open and reclose the circuit breaker of a generator by injecting a series compromised control commands. So when disconnected from the power grid, the generator becomes desynchronized. The Aurora attack is designed to reclose the breaker when the system and generator slip out of synchronization before the protection system responds to attack. So each time the breaker are reclosed, the difference between the frequency and phase angle between the main grid and the generator may result in high torque and current, so which can ultimately damage the generator. The second basically attack is press attack. The press attack basically is through the demand response program mostly. The press attack can send in the scaled value of the true price and delay attacks on the price signal. The attack increases mismatch between the generated and the consumer power. So the attacker is capable of injecting false pricing information at any moment and repeat over a long time duration. The power mismatch caused by the long-term attack can lead to power, overgeneration, economic loss, and poor power quality over there. The next attack is belongs to the control signal attack is wind shark attacks, again, wind turbine. As we know that wind energy or wind turbine is one major sources of renewable energy. So they also have SCADA system. We control the wind turbine and substation. They have communication and control functionality over there. The protocol they use is IEC 61425, which defines the communication requirement for the wind plant. The operator in the control room can remotely set on, off, and idle, and even perform the emergency shutdown procedure to stop the wind turbine. So the wind shark attack is basically for perform the emergency shutdown, which is AKA the hard stop repeatedly to induce excessive wear and tear on the critical mechanical component. So finally damage the wind turbine, as you can see from the middle figure in this slide. So next attack is measurement attack. So basically measurement attack is mostly targeted the power system estimation. Okay, measurement received at the control center, including a lot of information for the power grid, including the live power, bus voltage, and the current and magnitude, and the generator output, load, circuit breaker status, and such on. Okay, those raw data and measurements are processed by the state estimator in order to filter the measurement noises and detect gross error. So state estimation provide an optimal basically estimate of the system status based on available measurements and on assuming the system model. So we usually use the weighted WLS, weighted least square, is the most common state estimation method, and also we use bad data detection (BDD) in the state estimation to detect large measurement errors and attack. So the estimated state will then be passed on to the energy management system applications such as power flow, continuous analysis, and generation automatic control and stuff like that. The bottom left figure demonstrates the role of state estimation in system operation, and then we can also see the example, which is IEEE 14 bus systems. Dr. Liu will talk more details about the attacks and defense about the state estimation part. So based on state estimation, the false data injection attack is a highly structured threat with real world instance, as we mentioned before in this kind of incident diagram over there. So as shown in the right figure, the adversary usually maintain a foothold in the system and learn the system quite well for a long time. So FDI attacks inject malicious data into the SCADA system, and then they compromise the measurement and bypass the BDD, and resulting a bias in the estimated state. The estimated state will be used in the application later on, as mentioned before, such as the load estimation and OPF model. So finally, the FDI can adversely impact the grid operation, and energy market. So to inject a highly structured FDI attacks, the adversary usually need to have the knowledge of the system information. So another basically control signal and the measurement attack, which is we talked about before, categorized before, is Stuxnet-like attack. So Stuxnet-like attack is a type of control signal and measurement attack. So in this attack, attacker has a right access to both control signal and sensor measurements. And also the cyber physical system or smart grid is described as a discrete time, linear time invariant model, as you can see from here, the equation 1 and 2. Here, the U representing the control and the Y representing the measurements. The attacker can compromise U and Y at the same time. Stuxnet attack inject malicious control commands into the actuator. They corrupt the sensor readings to cover the ongoing attack and replay all the measurement during the steady state of the system. Such attack combine both control and measurement layer attacks to cause immediate failure and block the operator's awareness at the same time. So another basically control signal and measurement attack is line outage masking attack. So in this attack, attacker has right access to both the control signal and sensor measurement. Attacker can disconnect some lines from the attacked area through the remote opening the circuit breaker. As a line disconnected, power system will experience short-term disruption like voltage violation or line overflow. And then the attacker compromises the sensor and masks the measurements within the attacked area by DOS and FDI attacks. The attacker can launch DOS, such as the operator cannot receive the actual measurements in time, or attacker launch FDI attacks and replay the attacks to prevent system operating normally. So such attack can combine both control and measurement, again, can cause immediate failure and maybe potentially lead to cascade failure of the power system. So here I give you the block diagram of the line outage masking attack and how that can be implemented in the IEEE 39 bus system. Next, I want to briefly talk about the cyber defense approaches. So in our previous work, we briefly divided the defense approaches in the following category. The first one is security measurement sensors. This can incorporate tamper-resistant hardware to prevent unauthorized access, end-to-end encryption to protect data transmission, or data integrity measures like digital signature and hash function to ensure the authentication and prevent manipulation. The second one is basically maybe focus and later on is that data-driven machine learning approach, which is popular defense strategy. As we know that power system is not under attack most of the time. So there are massive amount of normal data for the machine learning algorithm to sufficiently learn. In addition, the construction of data-driven approach does not depend on the network topology for the power system. And also this approach is sensitive to the time variant measurements, which can be very effectively in detecting the FDI attacks created by the spatial relationship of power system. The next one, which is research focusing on our previous work, is moving target defense. moving target defense is an emerging concept which are widely used in traditional IT system. I'll get into that in the next slide. And also the watermarking is another approach. Watermarking is to inject known noises as a probe input to the system, and expected effect of such input should be found in the true measurement output due to the system dynamics. So watermarking can provide authentication and is effective against physical attacks or insider attacks who are usually have authenticated users. The next one will be hybrid approach. They usually basically form the defense in depth approaches by combining different approaches over there. The two-layer model in the right finger is a graphic form of the smart grid model to summarize the defense and mechanism. So I briefly talk about the moving target defense. Moving target defense is a concept originated in IT system. MTD basically is a concept of controlling changes across multiple system dimensions in order to increase uncertainty and apparent complexity of the attackers. This can reduce their window of opportunity and can also increase their cost of their probing and attack effort. MTD assumes that perfect security is not attainable. Given that as a starting point, the assumption that all systems are compromised will basically focus on enabling the continued safe operation in a compromised environment. We want to ensure that the system is defensible rather than perfectly secure. MTD is introduced in the physical layer of power system recently. So MTD basically can actively perturb the line impedance using the distributed flexible AC transmission system, a voltage regulator, smart inverter, such that attackers' knowledge about the true system configuration is invalidated. This diagram shows that a 37-node distribution system, which is equipped with MTD devices, such as defect devices and smart inverter. And in our previous, we proposed a comprehensive framework with 4 key metrics to evaluate performance of MTD in power system. Those metrics basically provide a structured way to assess and effectiveness and particularly MTD strategy. The first metrics is cost. This metrics consider both the capital cost of deploying MTD devices and the operational cost, including additional generation expenses and system losses caused by MTD. So understanding the economic impact of MTD is basically crucial for its feasibility. The second metric basically is detection. Detection is the most critical factor for any defense mechanism. So however, the previous research has not explored the connection between the detection effectiveness and power system operation planning. So our work basically demonstrates that the placement of moving target defense strategy between the planning stage plays a key role in determining the detection effectiveness. The next metric is stability. Since MTD operates by altering line impedance, it inherently introduces disturbance to the power system. So therefore, its impact on the voltage stability must be carefully considered to ensure the reliable and secure power system performance. The last one is stealthiness. Stealthiness is basically based on that a sophisticated attacker can detect the existence of MTD and adapt accordingly. So to prevent this, so moving target defense must remain hidden to the attacker to avoid the triggering countermeasurements. So this requires strategic and moving target defense, placement, and operation designed to maintain its stealthiness and effectiveness. So those 4 metrics basically have led to 4 critical research questions, as you said from this top of this slide. So how to optimally place defect devices, considering cost and detection, how to optimally determine the set point, considering operation cost, how we can adjust the defect devices to ensure voltage stability, how we can design a hidden MTD to smart attackers. So in the previous work, we have systematically addressed those questions and then through a series of publications. So the remaining of the presentation, I will hand it over to Dr. Liu, who is going to get into the nuances about his recent work. So I'm going to stop sharing right here.
Second, let me share my screen.
Okay, so. Oh, did I stop sharing? Okay.
Okay, in this section, I will present our work in the highly stealthy FDR attacks against the classic machine learning detectors. The supervised machine learning detector, they use historical measurements collected from the SCADA system as a normal data and use the FDR tags as a compromised data in the training stage. So classic machine learning detector can detect FDR attack based on the fact that normal data and compromised data, they tend to be separated in the certain projected space. Thus, the defender, they can conduct a PCA first to project high dimension data into the 2D space. And it is seen that in this figure, the normal data forms a cluster while the attacks located outside the cluster as outliers. In this case, these attacks can be detected by the classic supervised classification methods such as support vector machine, logistic regression, and multi-layer perception. But we know that this false data injection attack, they are designed to remain stealthy to the traditional chi-square detector in the estimation function. But this FDR attack is not designed to remain stealthy to the machine learning detectors. So our research question as here is, what is the limitation of these classic machine learning detectors? And how could attacker can smartly construct FDR attacks that they are highly stealthy to the machine learning detector and also have high impact on the power system operation? Okay, in our work, we propose a low-rank FDR attack. It is the first FDR attack designed to remain stealthy against the machine learning detectors and the chi-square by data detectors. So based on the low-rank property of the historical measurements, we applied matrix completion to make the compromised measurements consistent with historical measurements. At the same time, we maximize the incremental wattage to ensure the attack have sufficient negative impact on the power system operation. In addition, we construct this low-rank FDR attack using the incomplete network information. So we will define what is incomplete network information in future slides. And this proposed attack is stealthy to the chi-square detector because in our attack, we follow the physical law of power system. And this attack is stealthy to the machine learning detector because the attack generated by the matrix completion is consistent with historical measurements. So since we use matrix completion to construct FDR attacks, I would like to briefly introduce the matrix completion technique. Matrix completion is a technique aiming to estimate the unknown elements in an incomplete matrix that have low-rank property. So here is an example. We know that image is a matrix, right? So this figure of our brain is our original matrix. And then we randomly delete 70% pixels, then it becomes an incomplete matrix M. So matrix completion can take this incomplete matrix as input and estimate the unknown elements in the matrix. In this case, we can get the complete matrix X. So here is the formulation of matrix completion. It minimizes the rank of the complete matrix X and lets the elements in X equal to the known elements in the incomplete matrix M. To make the problem convex, the mathematical model minimizes the nuclear norm instead to formulate a convex problem. The question is how we can use matrix completion to construct our highly stealthy FDR attack. Since we use this technique, the first step is to formulate a matrix. We formulate a historical measurements matrix Z0. Here is a timeline. So SCADA system control center collects SCADA measurements every 10 minutes or 5 minutes. So from attacker's perspective, attacker keep collecting the measurements until T time step. And here each column, it is SCADA measurements collected at each time step, and different color represent different measurements type. Okay, until attacker have enough measurements, she will launch attack at the last time step. Assume attacker want to compromise this 3 bus highlighted by the green area, and the attacker need to compromise all the measurements related to the attack area. And we set these measurements to unknown, represented by this dot elements, and our matrix completion method will fill in these unknown elements. So before we present the low-rank FDI mathematical model, I want to demonstrate the trade-off between the attack stealthy and attack impact, and how the low rank have to achieve the balance. First, we use the SVM detector. It's trained to detect 500 FDI attacks, and then we project this 500 attacks into a 2D norm space. We call it this norm space because y-axis is a nuclear norm, and x-axis is L1 norm of the increased voltage. A smaller y value indicates the attack is a low rank, and larger L1 norm of the voltage bias indicate we have a high impact. And then the SVM detector is used to detect the 500 attacks, and all the detected attack is shown in left figure, and all the undetected attack is shown in red figure. In this case, red figure shows the attack stealthiness. Okay. So here is what we find in this figure. Let me use my pointer. And the FDI attacks with a small delta X value, small voltage injections, they are more likely to be stealthy. But since it have low voltage injection, it have low impact. Second thing we find out is when the voltage bias is large, they are more likely to be detected. However, attacks with low rank, they are more likely to remain stealthy because this rank is low, so it's more likely to remain stealthy. Here we will combine two figures together, and we equally divide the norm space into 16 blocks. And then we calculate the attack detection probability of each block. So a this larger ADP value, it indicates the attack is more likely to be detected by the SVM detector. So we can see here, upper left corner, they have a high ADP value, but a low delta X value, so that the attack falling into this area has a low impact and a low stealthy. On the lower left corner, his ADP is lower, so that attack in this area is low impact and a high stealthy. Similarly, on the upper right corner attack is high impact but low stealthy. And the lower right corner, it's a high impact and a highly stealthy because the ADP is low and the delta X value is high. So that's if we want to construct an attack with high impact and highly stealthy, we want our attack fall into this area. So how we can do that is we can minimize the rank of our metrics, measurements matrix, and also maximize the impact L1 norm of voltage incremental. So this from our objective functions of our low rank FDI attack. Okay. So if an attacker formulate historical measurements using all the SCADA measurements and want to integrate the physical law of power system, it requires attacker have the complete knowledge of the entire system, including the topology of entire system and the impedance of all the transmission lines. So it has a high requirements on attacker's knowledge. So this assumption could make the attack less realistic or less feasible. In addition, it will result in a very large historical measurements in the low rank FDI attack, which will cause some computation efficiency problem. Okay, so our solution is we focus on the local attack area of the system and build historical measurements using all the measurements related to the attack area. So in this case, it's resulting in a much smaller matrix Accordingly, the attacker's knowledge will be greatly reduced. So here we specify attacker's knowledge in our low-rank FDI attack. Here INI, incomplete network information, refer to the partial knowledge of local power system configuration. Specifically, attacker know the topology of attack area and know the impedance of most transmission line in the attack area, except several unknown admittance line. So here is an example for the INI in the 7-bus system. We use a gray area to represent the attack area, and the attacker aim to compromise bus 1, 2, 3, 4. And for the solid line, the attacker know their parameters. For this dot line, attacker don't know their parameters. Here, attacker don't know the line 2 and line 4 don't know their parameters. So this is a definition of the incomplete network information. So after we specify attacker's knowledge, we mathematically derive the model of AC FDI attack under the INI condition. This model provides the attacker with mathematical model to construct malicious measurements, ZA, using the voltage bias dirt XA under the INI condition. Here, H represents the voltage states to measurements mapping function is a nonlinear equations. And first, in our model, we linearize this S model by linearizing this nonlinear equation H. And here, H, capital H is a Jacobian matrix of small h functions. Since we calculate the directive of the power injection, power flow with respect to the voltage in H function, we need the line parameter of every transmission line in the attack area. But under the INI condition, we have unknown line, for example, line 2 and line 4, we don't know their line parameters. So we simply cite this conductance and the susceptance of unknown line impedance to 0 in calculation this Jacobian matrix. I will explain the reason later. For the bus on the unknown lines, for example, the bus 2 and the bus 3 on unknown line 4, we have some extra requirements. We want to inject an equal voltage angle incremental to these buses, and also we want to remain the voltage magnitude of these buses unchanged. In this case, the power flow, the active and reactive power flow on this unknown line will remain constant. Here, E times dirt theta, it represents 2 bars on this unknown line have equal voltage angle incremental. And F times dirt V, it indicates that their voltage magnitude remain the same after during the attack for these 2 buses. So these 2 equations ensure that active and reactive power flow on this unknown line remain unchanged in attack regardless of line parameters. In this case, attacker construction can ignore the unknown lines. That's why we cite the G and B susceptance of the line to zeros, because this ensures the power flow unchanged regardless the value of G and D. So we can use this model to generate FDR attacks. The benefit is that it reduces attacker's knowledge, and also it reduces the matrix size and can increase the computation efficiency. But in this model, we don't know the optimal delta X values. We will formulate a low rank attack to determine the optimal delta X values. When we combine the objective function we introduced earlier and derive the FDI INI model, we get our low rank FDI under the INI conditions. So in first two constraints, we define the compromised matrix ZA before attack is launched. ZA equal to 0, and when attack is constructed at time t, ZA equal to Z0 plus A. And the third constraint is the linearized FDI attack. It ensures that compromised measurements follow the physical law of our system. The following two constraints define the range of the malicious voltage incremental. Okay. Last, we integrate the INI voltage constraint from unknown lines. This bus should have the equal voltage angle incremental and the zero voltage magnitude changes. Okay, so here is our mathematical model for the low rank FDI attack. In this slide, we will show our case study in the HBE 14 bus system. We assume attacker aim to compromise the voltage of three buses. We define two scenarios. In the first scenario, attacker knows the parameter of every transmission lines. And in the second scenario, attacker don't know the parameter of the line 12. Okay, and in the low rank FDI attack, historical matrix is composed of local measurements of 200 time instance, and we launch 100 low rank FDI attack in each scenario. So that figure shows the normal states and the compromised states under the LR FDI attack. We can see that the voltage angle of three buses, they are greatly increased by the attack. And in the scenario 2, bus 6 and bus 12, they are on the same unknown line, so that these two buses have same voltage angle incremental is 0.02. While in the first scenario is a red line. Second scenario, these two bars, their incremental voltage are different. And red figures shows the normal and compromised measurements under the attack. The attack only compromised 26 measurements in the attack area, and we can see that even though we inject large bias, the attack didn't yield a distinct change in the measurements values, which can contribute to the attack stealthy against the machine learning detectors. Okay, here we evaluate the stealthiness of our attacks against the machine learning detectors. For the testing stage, we have generated 100 normal measurements data and generate 500 FDI attack under different attack magnitude. Okay, and we generate 100 FDI attack for each attack magnitude. In total, we have 5 different magnitude. And also we generate 100 low rank FDI attack in each scenarios. Then defender can apply the PCA on high dimension measurements with two principal components. 99% of the signal variance will be retained. So left figure shows that the projection of traditional FDI attacks in the testing site. Here, the blue star, they are the projection of the normal data in the training site. It serves as a reference. And we can see that the traditional attack with larger magnitude can be further from this normal cluster. Okay, and attack with smaller magnitude are more likely to remain inside the historical normal data. That's an attack with large attack magnitude. They are more likely to be detected by the machine learning detector. And the red figure shows the projection of our proposed attack. It's seen that this attack locates inside the normal cluster, so that the machine learning detector cannot detect them. The stealthiness of the proposed attack is evaluated by the machine learning detectors and some data-driven outlier detectors. Machine learning detector include in our case study include the super vector machine, sparse logistic regression, and the traditional artificial neural networks. For the outlier detector, we include the minimum covariance determinant and angle-based outlier detection, local selective combination in the parallel outlier, LSCP. We can see that left table shows the detection rate of traditional FDI attacks under 5 different attack magnitude. A larger attack magnitude will result in a larger bias. We can see that the SVM have the best performance best detection rate. It can detect 75% of traditional FDR attacks, whose R1 norm is 0.05. Red table shows the performance of detectors against our proposed attack. We can see that here the recall represents the detection rate. We can see that when the R1 norm of the voltage base is 0.07, which is larger than the traditional attacks, but for the SVM detector can only detect 0.6% of the proposed attacks. So this low detection rate and a large voltage bias indicate the attack is highly stealthy and has high impact. And also we conduct the case study in the HV118 bus system attack aim to compromise the voltage of 5 buses. So without our INI model, the attacker need a complete network information of the entire system, including the topology and also the line parameter of 186 lines. But with our INI model, attacker only need to know the impedance of 11 transmission lines. And also in our scenario 2, we can assume that attacker don't know 2 transmission line in the attack area, so that attacker only need to know the impedance of 9 transmission lines. So with the INI model, the matrix size is also greatly reduced. Without the INI model, the matrix size is 100 times 588, where 588 is the number of all the measurements in the system. But under the INI condition, the Z matrix become 100 times 40. 100 is time instance, 40 is the number of measurements in the attack area. And also we evaluate the performance of machine learning detectors under the low rank FDR attack. We can see that this attack achieved a low detection rate. Well, for the traditional FDR attack, they can detect like 75% of attack, which is consistent with our results in HV14 bus system. Okay, here's a and also now in our another work, we apply the tensor completion in attack construction, aiming to remain stealthy to the statistic detector and machine learning detectors. Here, tensor completion is a generalization of the matrix completion for high-order arrays. This tensor completion can allow one to explore the structure of the data that have multiple dimensions. This tensor completion can use the structure of all modes to improve the imputation of the missing entries. And we know that matrix completion is just a special case of the tensor completion. So similarly, we need to formulate a tensor first to conduct a tensor completion. Here, we formulate three third-order tensors that collect a SCADA system for t times step, t times instance. And the tensor takes the form of measurements times the bus times time. And this is a slab is a two-dimensional section of tensor. For each slab, x-axis is a bus index, y-axis includes the file measurements like the voltage magnitude, power injection, and power flow. So after attacker collect enough historical measurements, she can launch attack at the current time. And if attacker want to compromise the voltage of bus 3 and 4, attacker need to set all the measurements related to this attack bus to unknown. We use the red to represent the measurements need to be compromised. And this unknown elements will be estimated by the tensor completion. In the tensor completion model, we minimize the nuclear norm of a third-order tensor and also maximize the voltage bias. We convert the tensor to 3-mode matrix, Z1, Z2, and Z3. So the form of a third-order tensor is equal to the sum of the nuclear norm of 3 mode matrix. And also this constraint defined the known and unknown entries before and after attack. And the last remaining constraint set the voltage deviation constraints. So here we present the tensor nuclear norm of the traditional FDR attack using the black line, and our nuclear norm of proposed tensor attack is represented by this blue line. Yeah, we can see that our blue line can achieve a lower rank value, but FDR attack with a larger magnitude, they can cause a spike in the nuclear norm. And when the traditional attack and our proposed attack is projected to the 2D space, we can see that our proposed attack still located inside the normal cluster, but for the traditional attack, they will locate everywhere outside the cluster and can be detected by the machine learning detectors. So here we evaluate the stealthiness of a proposed attack using the traditional classic machine learning detectors and the statistical detectors. We can see that in the first table, the machine learning detector can detect more than 75% traditional FDR attacks. We can only detect for our proposed attack, it can only detect less than 10% of proposed attack. So that it shows that the our attack is stealthy to the machine learning detector. And also we evaluate the performance under the chi-square detector, largest anomalous, the residual detector, and the QSUM detector. Our attack is also stealthy to these static detectors. So this work identified two limitations of classic machine learning detectors. First, we found out that machine learning detector could not effectively detect an FDR attack with a small magnitude of the voltage injection, because when the injection is small, the compromised measurements caused by this attack is slightly larger than the noise, so that machine learning detector cannot detect them. Second, we found out that machine learning detector cannot detect the proposed attack with a large voltage injection, but remain the low rank value. This low rank value reflects the compromised measurements. They are consistent with a pattern of the normal measurements. Thus, the normal data and attack low rank data, they cannot be separate in the projected space and cannot be detected. This attack is designed for the machine learning detector, and the detection of these attacks, we can use the Dr. Wu just introduced the moving target defense, and also we can use the protect sensor to detect the attack. Because for the proposed attack, the first attack assumption is attack need to compromise multiple sensors. If system operator use protect sensors with a good strategy, then the attack cannot launch the proposed low rank attack. Second attack assumption is attacker needs a accurate topology or line impedance, so that if operator applies the moving target defense, they change the line impedance so that the proposed attack will be use the incorrect line impedance, and the attack will be detected by the by data detector. Yeah, that's all my presentation.
Right, thank you, Dr. Liu and Dr. Wu. Yes, I think there are some questions here. First question is that I think is for Dr. Wu. Can you give some realistic examples for MTD, FDI, or DUS? For example, for MTD attackers, they can inject reactive power or mislead the state estimation. How does this happen in the realistic?
Okay. So I think I will get started, and Bo can just add some comments. I think the Ukrainian, the 2015 Ukrainian attack, right? there is some, let me just go to the slides. Is one specific example for this. I think you mean the FDI attack, not the MTD. MTD is basically, we talk about the defense strategy. So let me see. Okay. Oh, sorry, I didn't share that. Yeah, anyway, I think the forced data injection attack has been in the past incidents several times. So they use the forced the measurements or forced injection attack can be replay attack, right? So as long as the measurement is not valid, it can be the historical measurements, can be any kind of manipulated measurements. So those are basically also can be categorized into the forced data injection attack. So like replace attack in the Stuxnet attack. So where the attacker control the the centrifuge spinning speed, and also they injected the old measurements from that the system. Those are basically can be categorized into the FD attack. Paul, do you have any comments?
Yeah, I don't have other comments.
Okay, good. Thank you. Yeah, the next question is from Napoleon. His question is, I think his question is for Dr. Liu. Is delta X determined by matrix completion, or can it be arbitrarily set?
Yeah, in the proposed attack, because we want to compromise the multiple buses, so the low rank attack help us determine the optimal delta X values to inject the voltage. So yeah, delta X is determined by the matrix completion. And in our case study, in the traditional FDR attacks, the delta X value is randomly changed.
Thank you. Yeah. If Napoleon, your question is answered, not answered, you can unmute yourself. Yeah, you can just let me know. So the next question from Mingzhi Zhang. Thanks for this very informative talk. I'm working on large-scale EV grid integration, and I'm curious if there are any real-world instances of cyber attacks on EV charging management network, and how they differ from cyber attack on the grid.
Yeah, so I take a first step on this question. So I think this is a very good question. So our current work and previous work basically focus more on this forced data injection attack, which is on the control center, either on the smart grid or microgrid, for the SCADA system. So for this EV charging management or network, so I read some article about there's some kind of cyber threats over there, but we don't have a look into specific or case or specific system into there. That's actually the maybe future research question we want to look into. Maybe collaborating with Dr. Zhang and other researcher over there. So, but I think the similar kind of the attack mechanism by injecting false data to maybe the manipulated measurements and or some kind of falsified control signal can also apply to the EV charging management or charging network. So as long as I think deal with this power grid. So that's maybe my our future work what we're going to conduct.
Yes, I heard that last year there are some inverter attacks for some P-ways in Japan. I don't know if you heard about this news or not. It's blackmailing the some monetary system for for money, not for the grid. But there are some attacks on the solar panel inverters. Yeah, that's maybe the first one in the world reported. Yeah, I think the EV attacks maybe will be happening. Yeah, soon.
Yeah, exactly.
Right? Yeah,
We
yeah.
have done some like similar work. We look into the PV CPS gateway. So we found some like cybersecurity issue with the existing or traditional the PV system. So basically, you can easily compromise the credential of the user. A couple of years back, they don't even use encryption for their communication. But I think now they do the patch and everything is encrypted. So, but anyway, I think there is some kind of cyber issues, and also we published some paper with Dr. Liu with some other cyber computer science researcher in KU, Kansas University. So we published some paper, identify the cyber threats or the vulnerability on the traditional PV related to, the microgrid or nanogrid. Yeah.
Okay, yeah, thank you. So, Dr. Wu, I personally have a question. How do also we have so many audience that are from universities and research institute, and so how do you usually simulate these various kinds of attacks? What kind of software do you usually use, and how do you have any suggestions for some of the students? How do they start their research on cybersecurity, since this is a very popular area?
Thank you. I think I would let Paul to take a first step.
Yeah, for the student, I think they can use like MATLAB to construct an attack and use a MATPower to generate the normal measurements data and just follow the FDI attacks equation, and then you can generate attacks. Yeah, based on my experience, and most of work is simulated inside the MATLAB. Another thing is we can use the hardware in-loop simulator to just run the attack model and the defense model and check their like residues, check their threshold, and determine whether attack is detected.
Yeah, I just want to add that's exactly. So it's really difficult to get realistic power grid data, especially those data under attack, which is really rarely to get. So what the research we do in university is that we do simulations, and based on MATPower, based on PSC, PSCAT. Those are basically the traditional tools we use power system analysis. We take a measurement directly from those software. And recently, we're starting to look into the OPRT hardware in the loop. So we use HyperSync as modeling power system, and getting some measurements directly from there. And actually, the measurements is directly from the communication channel, not which is maybe we can maybe see as a kind of mimic a real world communication protocol. That's actually the ongoing work which is happening in our lab at Kansas State University right now. Yeah.
Yes, great. Yeah, I remember we had a discussion on that. Yeah, I'm quite familiar with HyperSim, those stuff, because I worked for OPRT development.
Yeah.
And I look forward to visit your lab. Maybe
yeah, thank you
this year, next year. Yeah,
thanks so much.
Yeah, see
looking forward to. I know you are developing some similar OPRT over there, so looking forward to hear your progress in there. So
okay, thank you. Yeah, I saw another question from Wu. So can you share your ideas on effective detection of stealthy attacks?
cool.
Yeah, there's multiple detection strategies in the literature. First, you can use the protected sensors and determine how to place the sensor in the system configurations. For example, you can formulate like a spanning tree to cover all the buses. And also there's moving target defense, we have introduced how to place fake devices to introduce some uncertainties to attackers. And also right now there's a lot of application of deep learning method. Yeah, it's like CNN, RNN. Yeah, what I introduced is a classic machine learning in the detection. Right now, more deep learning method have been applied and combined together to detect attack. So it's kind of our future work to develop attack stealthy to these detectors. Another thing is right, and also like application use of the PMU device to detect attack. Yes, there's a lot of strategy there, and also use DER, how to introduce uncertainties, use DER to detect attack. Yeah, there's many directions using different software, using different hardware. Yeah.
Yeah, I just want to add one comment. I think believe in the future when we're dealing with this kind of a highly stealthy attack, the approach should be combined approach, right? Not only one approach. I think we mentioned before the moving target defense, maybe, and also the machine learning, combining with the secure measurements, combined with this watermarking and different approaches. We basically the defense in-depth approach. Basically, I think that's the way to go for the researcher to defend against persistent, against those kind of a highly stealthy attack, because those attacks can be very critical or have significant consequence to the power system. Yeah.
Okay, great. So yeah, I think that's it for today's presentation. For the audience, if you have more questions, you can feel free to send them to me. I can forward those questions to Dr. Wu and Dr. Liu. Okay, one more question. Why not? From the question from Kala. So can we directly utilize PMU measurements to find the attacks using machine learning and the DL method?
Yeah, there's multiple works using the PMU device to detect attack, but also there's some works show that PMU measurements are not safe. Maybe the PMU itself can be compromised by attacks. So it's going on both ways. PMU is applied to detect attack, but also there are several attacks targeted on the PMUs. So your measurements received by PMU is hard to say 100% free of attack if you use in the machine learning method.